So the purpose of using a potential relay is to disengage the start winding once it's up and running, so we don't overheat it and burn it out. So if you look, the contacts right here are in series with the start winding, because that's what we want to disengage, is the start winding, so they open or close. They're normally closed. The coil of the relay between 5 and 2 is in parallel with the start winding. So the coil operates because as the motor's running, that start winding generates a back EMF, which energizes that coil. It's a higher voltage that comes out of that start winding than the motor uses. The coil is a very high resistance. So what happens is, on startup, we have power coming in. Kind of like this. These are normally closed. I'll show you. So it kind of looks like that. It's running. Everything's good. So now that it starts, it's spinning. The start winding itself generates a back EMF, energizes the coil. Those contacts are now open. So the start winding is taken out. There's no flow through the start winding. Your power just kind of runs in like that through the run winding. Let's look at the actual relay. 5, 2, and 1. Notice 4 and 6 aren't here. 4 and 6, if you look, is just another, it's essentially a jumper, a dummy terminal. So you can feed that leg of power to your start capacitor, to your run capacitor, and to the run winding. Let's pull it apart. As we mentioned, the contacts normally closed. Can you see right here? Normally closed contacts as it's engaged. See if I can get in there a little better. Normally closed, they'll open up. So you can actually pinpoint between 5 and 2. This is one leg of 5. The wire is actually going to the coil. The other side comes out, goes to 2. And then between 2 and 1 is those contacts right there. So here's a potential relay trainer that's been designed over the years with all the common parts. We've got a compressor, our power supply, overload, the potential relay, a start capacitor, and a run capacitor. So we've got a diagram here that we were looking at, straight out of the Tecumseh handbook. Let's wire it up, and we can actually measure that back EMF that comes from the start winding and energizes this coil. Jordan, would you like to wire this up?
Sure.
It's nice because this trainer's, the alligator clips or the jumpers, they'll plug right into this meter. So we can go right across the potential relay and measure that back EMF.
2 hours later.
So we've shown you the diagram from the Tecumseh manual with the potential relay. So with all these starting components, the idea is to engage your start winding and then take it out once it's running. So we went over how the relay works. Coil is in parallel with the start winding, normally closed set of contacts. Once the motor starts spinning, the start winding itself generates a back EMF, which energizes the coil, opens up the contacts, and removes the start winding. We've actually wired up a handheld meter here, so you can actually see the difference across the coil when it starts. Check this out. You see the meter? 174 volts. That's the high voltage back EMF generated from the start winding. That's why it's wired in parallel. So that opens the contacts. Look at the voltage across the contacts when I start. Pretty neat, huh? If you look at this, we've got 121 volts from our plug.